Okay, so now understand the design process. I give you a rough example. Okay, for example, if you both want you to design a thermally driven cantilever beam for micro mixing application. Okay, so you both will tell you about only this sentence. Okay, now you need to think of what kind of ideal structure or possible structure it can be. So before I give you the structure, you might have some ideas already in your mind, right? Okay, maybe different from mine, that's okay. So my ideas, I think, oh, okay, if you want to do the cantilever beam. So my teacher taught me before, we're using bulk machining, okay? So we can take away all the materials under the cantilever and to form the cantilever beam easily. So there might be a good structure for me to start with. Okay, so once I have this cantilever beam by the corner attack effect, so the bottom materials will be etching away. So anyhow, I got a cantilever on the top of cavity. Okay, but it's only a static structure. It's no moving ability. So you want to fabricate a mixer. Mixer means we need to use that to do mixing, to mix two different liquid together. So it should be the dynamic devices, is not a static device. They should give some force, right, to move around and to give energy to a solution and for the mixing purpose. So in order to do that, we need to think of the way, what kind of way you want to use that to drive this kind of cantilever, to make them movable. Okay. So there are many different ways. Okay. But your boss tell you you want to use the thermally driven. That means you want to heat up the cantilever. Okay, in order to allow the cantilever to move, maybe back and forth, for example. Okay, maybe to move this rotating action. I don't know. Depends on what kind of things you like. Okay, so in this case, I think because we have a cantilever beam. So now we put the easiest way is to put the one heater on the top, okay? The heater can be applied by using the electrical heating method, okay? You can use different heating method, right? You can use infrared energy, using light to shine onto the cantilever to make it movable. This is still another different idea, using either static, using magnetic force, different kind of forces. But currently we're using thermal. And using the electrical thermal method. So we apply electrical energy into a heater, okay? Put the heater here. And when we heat it up, because of the heater, the material of the heater is polysilicon, for example here. And on the bottom, we have a cantilever. It's made of like a silicon nitride, for example. So these two materials have different thermal expansion coefficient, okay? So before you heat it up, the cantilever maybe just standing over there with a straight structure, no problem. And when we heat up the substrate, because the thermal expansion coefficient mismatch between the polysilicon and the silicon nitride. For example, the polysilicon is not as extendable as like the silicon nitride. When you heat it up, silicon nitride will extend more than polysilicon. So in this case, when you heat up the cantilever can curve up. Like I mentioned before, you have a polysilicon thing, you deposit many layers, you have a different stress, so they will curve up. But that's from the fabrication, the process of stress, residual stress. But this is different. This is we build up the temperature, okay? Heat up the substrate to make the expansion of the material differently, in order to curve up the structure, okay? So when heat it up, the structure will curve up. When cool it down, so it will come back. So we can repeat the process, okay? Again and again. So you got a flapping cantilever structure over there. It's dynamic structure. It's like an actuator, okay? So this is a rough idea. So now, until this part is only the pre-design, from the idea specs into the pre-design. when you have this kind of idea and also draw very rough structures over here, actually, until this point, you still don't have any dimensions, right? You don't know how long the beam is, how wide the beam is, how thick the beam is. You don't have that dimensions yet. You have only the rough idea to see the principle is workable, useful, right? But it sounds very logical, right? I think it's okay. Yeah, it might be useful, might be applicable, okay, so far. Even is no dimension here yet, but you think the idea is reasonable, okay? So that's the first step. So now want to do the second step. So once you find that this structure is reasonable, then you want to go to the detailed design about the dimensions. Otherwise, how can you fabricate the things? You don't have a dimension. How can you have a structure? So you got to consider the dimension. So now you need to consider the specs. So you both only give a micro mixer, okay? However, they did not define how fast the mixing effect the mixer can provide, and how large the force, how fast the flapping, those kind of things. No such kind of information. And also, the materials is chosen by yourself, right? Currently, you are choosing, not you, I. I'm choosing polysilicon and silicon nitride. So they will give another question about what kind of temperature this structure can sustain. It's still working, right? If you have a temperature too high, it will burn out easily. So you have a lot of limitation over there. It's not that simple. So those will give you constraint for the final dimension of the structural design. Okay. So for example, if I want to, actually we will do more detailed analysis later on, so not here. Okay, just give you a rough idea. So according to the materials mechanics, okay, they will tell you if you want to curve up the structure into what kind of degree or what kind of levitation depth, you need to give how much force or how much stress into the beam. So according to that stress information, you can apply the thermal expansion coefficient, this concept, to calculate the temperature difference you want to give in order to get expand the beam long enough to curve up enough for this kind of action. Okay, so now you will find this kind of consideration and there's some equation calculation. You will find out, oh, I want to design this device between room temperature up to 150 degrees. So now you have a 125 degrees C differences. So that differences, temperature differences, will give you like a 2 micron levitation of your tip, the deflection of the tip. Okay. Then after this kind of information, you will consider, oh, I want the beam flap faster, above like 1 kilohertz. We want to make the mixing more efficient. So for 1 kilohertz, that means you need to calculate the frequency response. You find that the beam cannot be longer or larger than like 1 millimeter. Otherwise, the frequency response is usually lower than 1 kilohertz. So that's giving you a limitation. The temperature also gives you a limitation. So you got a lot of constraint. The constraint in the design map like a contour, like a boundary. So you design you want to draw a basketball into the basket, okay? So the basket is your design constraint. You have a lot of design constraint. You want to throw your ball into the basket, not outside the basket. That's why basketball meaning, right? Why basketball mean? So so you have a lot of design constraint. Like I just mentioned, you have a temperature constraint. You have a speed constraint. You have the deflection constraint, those kind of constraints. So you put all the constraints together, they will form the basket, the boundary. So you just throw the ball inside the boundary, not outside the boundary. Okay, understand? Okay. But if you are not experienced, you may design, you may give the constraint too severe, too vigorous. in order there will be no basket form between. In that case, the design will be no solution. That's very typical for beginner. So that's why to define the specs is not easy. So you need to have some experience to define the specs. Okay. So after that, the design specs and okay, for example, the frequency at least 1 kilohertz and 400 degrees C, 4 micron, 20 micron square. So now also we have another constraint. We don't want to fabricate the device too large because we have a limited space, okay, for the whole structure to work with. So usually we'll give a limitation on the final size. Cannot be larger than a specific area. Save money. Yeah. So the chip space is like a real estate. You know, real estate. You buy a house, you cannot buy an extremely large house. Yeah, it's very costly. You need to spend all the money into a small area. Try to make your house functional inside a small area. Okay, that's the idea. So also the total area need to smaller than some kind of area. There's also a constraint. So those aspects will give the guidelines constraints and the basket for your basketball. Okay. Okay, so now you got all the constraints. So and you need to adjust. Actually, for the design, you cannot accomplish a design in one step. Not possible. I will tell you. It's a painful process. You need to adjust it back and forth. Sometimes you want to make a longer beam to make the diffraction larger, right? But you reduce the speed at the same time. So you need to trade off between them. Try to find out the right length for good diffraction and also with good speed. So it's not possible to guess the right dimension at the first time. No, that's not possible. So you need to gradually tailor your design, case by case. So now go to the simulation part. So that's why not only one design you will give out for this kind of specs. You may have different kind of designs, a series of designs. For example, 5 different designs. So these 5 different designs, which one can give the best performance? Actually, you really don't know before you fabricate them. So in this case, it will be better for you to do some simulation. Okay, before you do fabrication is a very time-consuming process. So if you don't have the tool of simulation, the only choice you have is to fabricate all of them and do the final testing and find out which one is better and try to optimize the structure. But if you have a simulation, you have a tool, they will help you to define the final structure much faster, maybe in 1 month, 2 months, if you are very familiar with the software. Okay, so that's the meaning of the simulation, the pre-design. So you got several different structures and designs, dimensions, then you do the simulation, and you find out which simulation results the performance is the best to select from them, and use them for your final fabrication. So for the fabrication, you also need to consider the fabrication process. And if you have like for example, you originally have 5 different structures. After pre-design the simulation, you found out only 2 or 3 of them are reasonable according to the performance. So you try to select these 3 as your final candidates, okay? But before you go to the real fabrication, now you need to consider if these 3 candidates can be fabricated by the currently available process. Sometimes they may not fabricate it at all. For example, if you have 3 this kind of candidates, one with a very long cantilever, for example, like 1 centimeter long, you can give the performance 1 centimeter long. But the other one maybe only 1 millimeter or shorter, but has a wider beam. Okay, it's a different design. Okay, so we found out the fabrication process because of stiction problem, we just mentioned the surface micro machine process, the final step, want to release the structure. The stiction will damage your structure. You found out during the fabrication, the length of the structure cannot be larger than 1 millimeter according to your current ability for releasing process. For example, if your lab you don't have the very good releasing process called the supercritical process. The supercritical process can help you to maybe release a more than 1 millimeter long beam. Okay. However, if you don't have this in your lab, you have only alcohol and water and heater, these three things. So the maximum length you can fabricate for the cantilever is only 1 millimeter. So these three candidates, you need to drop one, the longest one. You have no choice. It's not fabricable. Although he passed all the design criteria, but it's not fabricable. So you need to drop it. So end up, you have only 2 candidates for fabrication. Understand? Okay. So you have a lot of design originally, but according to different steps of screening process, you end up only have several in hand for the final fabrication. Okay. So fabrication process is also one of the criterion for you to screen out the not suitable design, non-suitable design. Okay, and there are some other criteria like packaging. Sometimes it's not easy to packaging, for example. Okay, so you need to consider packaging or IC integration as well. Okay, for the process. Okay, so after all this screening process, now you have the final structures with the dimensions, and now you can draw them into a real structure. We call it layout. Like you want to build up the building, right? So each floor, you need to have a layout to define which one is your bathroom, which one is your living room, which one is your kitchen, right? We call this a layout. So same as this main structure, you need to design to really draw them down, okay, into we call the layout. So you have the dimension of those structures. So you want to draw them onto by using the software onto the real ground, and layer by layer, okay? Because the fabrication is a masking, one mask by one mask. So different material that means they are on different masking level, okay? So when you do the layout drawing, layout design, actually you put all of different material together, become a device, right? Because you want to know the relationship between the pit structure and the cantilever, your heater. They have a fixed relationship to each other, right? So you need to put them together to find out if they are at the right position you want to put them. Okay. However, during the fabrication, you are not doing the fabrication at once. For the 5 materials fabricated together on the same level, it's not possible. So you need to do the fabrication layer by layer. So the layout software has one ability. After you draw those material structures onto the ground level, they stack together on one level. But the layout software has the ability to separate them into 5, for example, 5 material into 5 different levels of the mask structure. So anyhow, you have 5 masks, each mask corresponding to 1 material. Okay, so you will fabricate 5 masks. Then when the mask come back, you will do the fabrication 1 mask by 1 mask. Okay, after finishing 1 mask, then do the next mask, do the next mask. So you will do the deposition of the material or do the etching of material. After finishing 1 mask process, then do the second mask process, layer by layer, build them up like a building, similar to a building. 1 layer, 1 floor by 1 floor, you build up your structure. Okay, so that's the final steps. Okay. So there are different design concerns. Okay, so actually in this lecture, in this course, okay, throughout the semester, we will focus on two things for the fabrication, for the design of the fabrication, and the idea of fabrication. So one is called microsensors. So we will use one example, one accelerometer as example, and also actuators, one actuators. So we will use a contract actuators as an example to introduce you about the detailed design process. And in this course, we don't give you the design idea about the fluidic systems, thermal fluidic systems. So for this design, I encourage you to consider to take another course. I'm going to give in the next semester, the micro-nano-fluidics and the biosystem design. So in that course, I will talk about the fluidic system design. Okay. Now we come back to the microsensors. What kind of a consideration you want to keep in mind when you are doing the design? So for microsensors, there are many different kinds of sensors, including physical, chemical, biological, different kinds of sensors, mechanical. So first, you need to consider how to operate the sensor. The sensor means we get the signal from outside. We change the energy from outside into the signal, the energy we can do the detection. Most of them are electrical signal for detection. So for sensors, operational principle like using what kind of piezoresistive, like a capacitive or tunneling, different kind of methods. Actually, in this course, I will introduce only one operation principle, piezoresistive. You want to understand more than this kind of operation principle. Actually, there are another course, microtransducers, okay, which will be offered by, I think, P&E department. I don't know, Professor Liu is still teaching this course or not. If it's the case, you can take them. You can take this course. It gives more wide spectrums of the different kind of operation principle. So in this course, we are not focusing on different kind of principle. We just give you one idea how to go through the whole design process. So once you understand the whole process, you can apply this kind of fabrication process, design process to other different kind of operation principle. Okay. So then the process feasibility, you want to use in IC process and then bulk memory machine, surface memory machining process, liga, molding, plating, different process. Okay, these are the first two are operation principle and the fabrication process. And for sensor, important aspects we usually mention is about the first one is the responsivity. Responsivity means the response of the sensor to input energy. Okay, the input energy can be a different kind of format. For example, like a physical energy. For example, like a accelerometer. For accelerometer, the purpose of accelerometer is to use the accelerometer to detect the acceleration. So when you have an acceleration of the device onto the device, okay, the structure will be deformed because acceleration will give force actually. The force will deform your structure. So if you have some kind of method to detect the deflection of the structure, deformation of the structure, you are able to make this become a sensor. So the responsivity means when I give you the fixed acceleration, how much output signal you can get from the sensor. Okay, the ratio means responsivity, the response. Okay, responsivity. So if the responsivity is high for a sensor, that means the sensor is more more sensitive. I don't want to use the word sensitive because sensitivity is a different term. But you know the idea. It's more sensitive to this kind of energy change. Okay. Okay. So this first thing is responsivity. The second one, we'll talk about the sensitivity. The sensitivity usually will misunderstand with like responsivity for a sensor. But sensitivity in sensor, the definition is different. Sensitivity means the minima signal you can detect. What's the minima signal? The minima signal a sensor can detect usually is a noise floor. So the sensitivity means the noise. What's the maximum noise? Well, sorry, what kind of noise you have in the sensor system? So your signal need to be above the noise. Otherwise, you cannot do the detection. Okay? So the signal will be buried inside the noise. You cannot detect them. Okay, so the noise floor, we call it sensitivity. The third one we usually concern is about the frequency response. Frequency response means the speed. How fast, okay, the sensor can respond to energy change. Okay. So if the sensor is not responses that rapidly, for example, I give a punch on your shoulder, okay? So if I punch fast enough, you won't feel anything. That means that your sensing mechanism is not fast enough to respond to my punch, okay? So different sensor design have different, the frequency response. There's a mechanical, properties. I will tell you in more detail later on. So how fast the sensor can respond. If a sensor is not fast enough, some quickly change the signal, you cannot do detection. Okay. And we also talk about dynamic range. Dynamic range means how much different signal, the larger signal you can detect divided by the small signal you can detect, the range. Okay, we call dynamic range. And also others like limitations, shock resistance, Q factor, quality factors, more details. And I'm not going to give it too much detail right now because it will confuse you a lot. So just keep in mind the four importance in responsivity, sensitivity, frequency response, dynamic range. These four. I think these four are the most important four. How you understand them. Others we will talk about then a little bit a little more later, when we have those questions encountered. Okay. And for actuator, they are a bit different. In addition to operation principle, process feasibility, we consider actuator the most important is the output force. Is similar to the responsivity to microsensors. The output force, output energy, output power is the first measure of the property of a good actuator. So if an actuator is good, it can output a lot of energy, output a lot of force. Okay? And also frequency response, dynamic range, those things are similar to the sensors. The difference is the sensors is for taking in the signal, taking the energy to give the signal. Actually, is taking in the energy to give out the force. So the difference between them. Okay. Okay, and other like fluidic systems are still we will consider like a flow rate, those kind of flow related properties, and also efficiency, accuracy, leakage, those kind of things. It's different from sensor actuators. So yeah, we will not talk about more in this course, but you will have some idea if you take another courses, which will be offered by me next semester. Okay, so we stop here for break. So we will continue for 10 minutes later. Thank you.